The primary focus of this forensic investigation is the final surviving example of a specific early variant dive bomber. The aircraft is formally identified as Bureau Number 1612. Archival manufacturing records confirm this specific airframe is the 17th production model built in its series. It currently stands as the sole surviving variant 1 aircraft of its type in existence. The operational history of this airframe began with its initial delivery to the United States Marine Corps in September 1940. During this period, the aircraft represented the baseline configuration of naval strike aviation. However, the rapid acceleration of military technology rendered this early production model obsolete for frontline combat. By 1942, the military command transferred the aircraft out of the combat fleet. It was reassigned to the Carrier Qualification Training Unit stationed at Naval Air Station Glenview. This transfer fundamentally altered the operational risk profile of the airframe. The training command required student pilots to execute continuous repetitive practice flights. The fundamental constraint of this training program was the Navy's decision to conduct carrier qualification in the protected inland waters of Lake Michigan. The lake removed the threat environment of the Atlantic and Pacific coasts while still giving student pilots a moving carrier deck, wind, water, and the operational discipline of shipboard aviation. Flying over open freshwater also stripped away many ordinary land references, increasing the workload on young pilots. But the essential task remained visual carrier qualification rather than blind instrument flying. The military decision to use older Variant 1 aircraft for this hazardous duty was a deliberate operational trade-off. Deploying the obsolete airframes for student training preserved the newer combat-ready variants for active theater deployment. As a direct consequence, the older airframes absorbed the physical penalties of high-cycle training use. The structural stresses of repeated landings, wave-off attempts, and student pilot error were concentrated on these specific training aircraft. On November 21, 1942, according to the Navy loss records cited by later researchers, the aircraft launched into this high-risk environment. Some later project descriptions have repeated a different November date, so the surviving archival record should be treated as the stronger point of reference rather than a perfectly frictionless timeline. The pilot in command was Ensign Herbert Welton McMinn. Archival records confirm he was 24 years old at the time of the flight. The flight placed him over Lake Michigan inside the same carrier qualification system. The military monitored these flights using strict time intervals and endurance limits. The definitive operational boundary was fuel capacity. When the aircraft failed to return, the procedural status of the flight immediately escalated. The military officially declared the aircraft overdue at exactly 1100 hours. This time marked the transition from a routine training operation to an active emergency response. The training command immediately halted standard operations and initiated a massive surface search. The search parameters were defined by the last known operational sector and the projected fuel exhaustion radius. For a continuous period of 12 days, military ships and aircraft scoured the surface of the lake. They executed precise grid patterns to maximize visual coverage. The search teams were looking for floating wreckage or fuel slicks or any sign of the missing pilot. A 12-day operation represents a massive expenditure of logistical resources and manpower. The wreck evidently sank before searchers could locate a useful debris field, but the exact sinking mechanics were never documented. The surface search teams were limited to looking for objects that retained positive buoyancy. Without floating debris, the search grid expanded into a vast empty space. Despite this rigorous effort, the surface search yielded completely negative results. Investigators found zero trace of the aluminum airframe. They found zero physical evidence of the pilot. The primary objective established by the military was to locate the physical wreck and verify the status of the aircrew. The complete failure of the 12-day search meant this objective could not be met. The historical record was sealed with an unresolved gap. The specific mechanical failure or human error that caused the aircraft to go down remained entirely unverified. This gap in the physical evidence would remain undisturbed for decades. The total absence of surface debris indicated that the aircraft had penetrated the lake surface and sunk to the bottom. The exact sequence of the 1942 impact remains undocumented. Archival and restoration evidence confirmed that this early variant lacked the armor protection and self-sealing fuel tanks installed on later combat models. That structural difference matters historically, but it does not establish a precise flooding sequence. Once the aircraft struck the water, impact damage, seams, openings, and unsealed internal spaces could have allowed water into the wings and fuselage. As the airframe settled lower in the water, flooding through impact damage, seams, openings, and unsealed compartments would have increased the aircraft's weight and reduced any remaining buoyancy. The heavy engine and forward fuselage may have helped pull the airframe beneath the surface, but the precise balance of impact damage, flooding, and attitude in the water cannot be reconstructed from the known record. It then came to rest in the sandy, muddy sediment of the lakebed. For the next 52 years, the aircraft remained entirely submerged in this specific environment. The location was approximately 5 miles off the north shore of Chicago. This geographical placement isolated the wreck from casual discovery or accidental interference by commercial shipping anchors. The environment surrounding the submerged airframe became the primary factor in its survival. An aircraft lost in a saltwater ocean environment faces immediate and aggressive chemical destruction. High salinity water acts as a highly conductive electrolyte. This accelerates galvanic corrosion across all dissimilar metals within the airframe. Furthermore, marine biological organisms rapidly colonize submerged structures in the ocean. These organisms consume organic materials and secrete compounds that weaken aluminum alloys over time. The cold freshwater environment of the deep lake presented a completely different chemical reality. Low salinity reduced galvanic corrosion compared with a saltwater wreck site, while cold bottom temperatures slowed chemical reactions and biological processes. Sandy, muddy sediment partially buried heavy sections of the wreck, limiting water movement and oxygen exposure in some areas. These conditions preserved enough of the aircraft's geometry for the fragile aluminum skin and internal bulkheads to remain identifiable. The flooded airframe also avoided the mechanical load of holding a large internal airspace against external pressure. The absence of self-sealing tanks remained visible as a configuration feature, not proof of the full sinking sequence. The result was not stasis, but unusually strong freshwater preservation, with corrosion slowed rather than erased, and the evidence hidden completely from visual observation. The question remains how investigators can isolate a precise aluminum structure against miles of flat, sandy sediment. The search for the missing aircraft resumed in 1994 using advanced acoustic technology. The recovery team established a new operational objective to locate the exact position of the wreck. Archival research provided the foundational data for the search. Investigators analyzed the original 1942 flight schedules and the boundaries of the carrier qualification training zones. They translated these historical documents into a rigid geographic search box over the lake. The vast area of the lakebed required a sensor system capable of sweeping large swaths of sediment rapidly. The team deployed a side-scan sonar system to map the bottom contours. The sonar towfish was pulled behind a surface vessel at a calculated depth. The physics of acoustic mapping rely entirely on sound wave reflection. The sonar emits continuous pulses of high-frequency acoustic energy directed down toward the lakebed. When the acoustic energy strikes the flat, sandy mud of the bottom, it reflects a uniform baseline signal back to the receiver. This creates a flat acoustic map of the sediment. The sonar shadow geometry dictates how a foreign object is detected. When the sound waves strike the dense metallic surface of an aluminum wing, they bounce back as a hard concentrated return. The solid metal blocks the sound waves from traveling any further. This blockage creates a distinct area of acoustic shadow immediately behind the wreck. The length and shape of this shadow are mathematically proportional to the height and geometry of the object standing off the lakebed. By analyzing the hard return and the corresponding shadow, the sonar operators can measure the exact wingspan and fuselage length of the target without ever seeing it visually. On March 29, 1994, the acoustic sensors registered a major anomaly. The sonar display revealed a hard return and shadow consistent with an aircraft-sized metallic target resting on the lakebed. The target was localized within the projected historical search box. The acoustic evidence did not by itself prove every dimension or identity with mathematical certainty, but it gave the recovery team a strong, testable target. The match between the 1994 sonar target and the 1942 archival search data validated the search methodology. The isolation of this target against the broad lake bottom demonstrated the effectiveness of side-scan sonar for locating submerged aircraft wreckage. This localization forced an immediate procedural shift from remote sensing to physical intervention. The original 1942 loss involved a missing pilot. The strict forensic protocols required the recovery team to execute a verification dive before any recovery operations could begin. The divers descended through the cold water column to visually inspect the site. Their primary objective was not salvage, but forensic clearance. They reached the lakebed and identified the specific structural details of the airframe. The identification of Bureau Number 1612 depended on the convergence of evidence: the historical search area, the aircraft type, the early configuration features, and the records tied to the missing SBD-1. The absence of later self-sealing tanks supported the early variant identification, but it was not, by itself, a serial number proof. The divers examined the open cockpit section. They conclusively verified that there were no human remains trapped inside the fuselage. This physical inspection resolved the immediate human remains question at the wreck site, but it did not erase the legal and preservation responsibilities surrounding a naval aircraft wreck. Any recovery still depended on authorization, stewardship, and conservation planning. The missing status of the aircrew was resolved only with respect to the wreckage itself. The operational focus now pivoted toward the extraction of the fragile structure. The engineering challenge shifts to how a flooded, weakened airframe is brought through the surface interface without structural collapse. Discovery now gave way to extraction, and the immediate hazard was any direct vertical lift that would expose the fragile, waterlogged airframe to sudden, unsupported weight and surface motion. Although the cold water had preserved the aluminum, the metal had still been submerged for decades. The internal cavities of the wings and fuselage were entirely flooded and packed with heavy, dense sediment. The primary constraint governing the extraction was the dynamic wave load at the surface. The lake surface is constantly agitated by wind, creating continuous wave action and surface chop. If the team lifted the flooded aircraft directly through this turbulent interface, the structural physics would change violently. As the aircraft broke the surface, the surrounding water would no longer support its weight. The thousands of gallons of water trapped inside the wings would instantly become a massive internal deadweight. Simultaneously, the external wave action would strike the exposed aluminum panels. The combination of dynamic shock, loads from the waves, and the extreme internal weight of the draining water would easily crush the weakened airframe. The wings would buckle, and the fuselage would snap under the combined stress. To prevent the destruction of the historical artifact, the team implemented a strictly controlled submerged tow protocol. The engineers designed a rigging system to lift the aircraft out of the gripping mud without breaking the surface. They rigged the aircraft carefully under controlled recovery conditions, spreading the load across the strongest available structure without treating the wreck as a single solid object. The crane carefully hoisted the wreck just high enough to clear the lakebed. The crucial decision was to stop the vertical lift while the aircraft was still submerged. The entire structure remained suspended completely within the water column. By keeping the airframe underwater, the team neutralized the internal weight. The buoyancy of the surrounding water continued to support the heavy flooded wings. The tow vessel then engaged its engines and began pulling the suspended aircraft slowly horizontally through the water. This submerged tow isolated the wreck from all surface wave energy. The trade-off of time and navigational complexity was absolutely necessary to ensure the physical survival of the artifact. The tow vessel had to maintain a constant speed to prevent the airframe from swinging on the lift cables. The drag of the water against the airframe had to be carefully managed to avoid tearing off loose panels. The tow vessel navigated the suspended load away from the open chop of the lake and steered toward the shoreline. They directed the tow into a sheltered local marina where reduced wind and wave action made the final extraction possible. The shore-based crane lifted the airframe through the calmer interface. The controlled lift allowed internal water to drain more gradually and reduced the destructive shock of wave impacts. The structure was successfully placed on the dock. Once the airframe reached the sheltered marina and dock, preservation risk shifted from water recovery to logistics. Overland transport required immediate disassembly. The wings were detached from the center section, the tail surfaces were removed, and the unified aircraft became dozens of vulnerable components. Without the support of the assembled spars and joints, bare metal sections could flex, deform, or lose small forensic details each time they were lifted, strapped, stored, or moved. Over the next 27 years, the disassembled aircraft passed through several museums and institutional hands before reaching its final restoration home, with each transfer requiring renewed handling, storage decisions, and documentation of fragile aluminum parts. Across 5 institutions, archival control became as important as physical handling. Every panel and rivet line had to be documented so recovered parts were not mixed with components from other aircraft types, while storage conditions introduced new stresses, temperature and humidity fluctuations, atmospheric cycling, stalled conservation priorities, and lack of dedicated restoration space. What began as temporary transport disassembly became a 27-year chronic condition, leaving the sole surviving variant 1 dependent on a restoration environment capable of stabilizing, inspecting, repairing, and reassembling the fragmented airframe without imposing new damage. The chain of custody friction finally terminated in 2021 when the disassembled components arrived at their final destination. The transfer to the specialized restoration facility at the Air Zoo marked the beginning of the final conservation phase. The engineering team was immediately confronted with the physical consequences of the 27-year delay. The aluminum shell of the fuselage had warped significantly during its time in scattered storage. The bare metal sections could no longer be simply bolted back together. The team had to design a structural intervention to save the airframe from permanent distortion. The core constraint was controlled access to a fragile, incomplete fuselage. A bare aircraft structure cannot be treated like a rigid, modern artifact. To solve this, the restoration team used a specialized rotisserie-style jig that supported the fuselage from the firewall to the tail and allowed technicians to rotate the structure safely during work. The jig helped the team reach rivet lines, repair damaged sheet metal, inspect corrosion, and conduct the detailed metalwork required for restoration. Instead of forcing the aircraft back into shape in a single dramatic correction, the frame provided controlled support while conservators worked section by section. With the fuselage supported and accessible, restoration could move from structural stabilization toward the aircraft's final appearance. The airframe was restored in its distinct pre-war markings, including the yellow upper wing surfaces associated with the Navy's Yellow Wings era. This paint application restored the visual language of the early Variant 1 configuration while leaving identity anchored where the investigation had already placed it. In the bureau number, the archival record, the recovery history, and the surviving structure. The conservation of Bureau Number 1612 secured the 17th production airframe well enough for restoration to proceed in a recognizable early production configuration. However, the physical evidence still imposes a hard limit on the historical narrative. Restoration can stabilize the metal and return the aircraft's outward form, but it cannot recover the missing data from 1942. With no flight recorder, no direct testimony from the site, and no verified accident sequence, the definitive cause of the loss remains beyond the reach of the surviving evidence. The documentary record ends at that boundary.